I'm Dr. Shane Johnson. Good morning, everybody. How are you? Hope you're doing well. Today we're going to talk about moments, moment resultants, how to calculate them, how they come about, and we're going to talk about how easy it is to go through those calculations if you know the external forces applied, what points they're applied at, and a bit of geometry. So let's get into it, and I'll start by introducing a little bit from the PowerPoint, and then go into doing some calculations. So I hope that you enjoy the lecture today. So Chapter 3 begins with force system resultants and moment system resultants. And so let's get started here. So one of the things that you can find when you're working on a car or on an auto part or any type of mechanical system is that we apply forces, and those forces result in torques, moments, some type of twisting action about a body. So as we apply, I hold onto the one side like in this problem, and I'm going to take the wrench and tighten it with the other. So I'm torquing down that nut on the bolt. Holding that bolt, torquing down that nut on the bolt in this case. And I have to apply a force couple, so forces in two different axes to turn that nut onto the bolt. So how do we describe what happens there? How do we describe the forces that are inside? So one of the ways that you can imagine it is, let's try to simplify, get rid of all the other parts of the problem. So you can see on this one, we have the nut or the other side, the bolt on that side, and then we have our wrench, and we're applying that force, right? We're applying that moment to turn that nut onto the bolt. So what's really helping us to turn that nut is that force times a distance. So that gives us the moment. So we call that FD. So the moment is equal to the force times the distance that we apply. The moment would then be higher if we applied a larger force with the same distance, or if we applied the same force with a longer wrench and put our hand out further on that wrench. That's going to give us more force. It's not just that, though. There's more to the science than that. So the first thing that we want to do, when we get started, is to say, let's just take our thumb and we put it about the axis that we want to rotate. In this case, that's about 0.0 in the z-axis. We put our thumb about that axis, and I take my fingers and I curl it in the direction that the force is applied. And you can see in this case, my thumb is pointing in the positive z, and the force is applied perpendicular to the member, and it's going to help to turn that wrench about the z-axis. So you can try to do that by yourself. So we always try to get a sense of which is the axis of rotation by taking out our right hand and doing the right hand rule to determine the axis of rotation. In this case, the z-axis. So let's say I had applied that force at some other angle than 90 degrees. For example, some angle theta. So in this case, not all of the force would it be transmitted for torque. There's some component of this one that's just pulling along the length of the wrench. Well, that part that's pulling is really not helping me for torque, right? I want to calculate this new perpendicular distance. That would be d sine theta. Now, another way I could do that is I could say, well, there's two components of F, right? We have the force that's along the length of the wrench, and we have one that's perpendicular to the wrench. So that would be F times the sine theta times d, or I can do d sine theta times F. Either way, I'm going to get a distance and a force. And there's a nicer way to write that if we want to use vectors. to be able to show how to do this. Now, you could easily see that the force that I apply along the direction of the wrench is really not giving me any torque. So again, I would put my thumb in the direction of the z-axis that I'm desiring to have torsion about, and I can't really curl my fingers in any direction. There's no perpendicular direction to the wrench. So it's just not going to give you any torque there, right? So so this wouldn't be helpful. And let's say if you had a door or a wrench, you wouldn't just pull on the door to try to get the door to turn, right? You'd apply some perpendicular force to the axis of to the surface of the door, right? So when we're working out these problems, the easiest way to find that perpendicular distance to the force is to do the cross product, right? So R cross F. So while in the previous few slides we showed that you can do the moment is equal to F times some perpendicular distance d sub A in the first equation here, the easier way of looking at that is that you say M about some point O is equal to R cross F, or the moment resultant due to several forces is equal to the summation of R cross F. And so you can see in the lower left diagram here that we have F1 times D1 is equal to M1. F2 times D2 is equal to M2. F3 times D3 is equal to M3. And I can just add M1 plus M2 plus M3 together that way. Now, another way that I can do it is R cross F if those forces were not applied perpendicular to that distance vector. So this is the equation, and it's relatively easy to calculate how different forces can be applied to have a force resultant on a body. Now, the right-hand rule is used in this problem, and so you can see the moment O in the upper right-hand side. I put my thumb in the axis of rotation. I curl my fingers in the direction of the force, and you can see I'm applying a torque. That's in this case it would be like a positive torque. You can have some sense of rotation. Now it's helpful to identify which is my positive x, y, z, so I know if I have a positive I, j, or k moment in those respective axes. So that's what we're going to do in just a little while. But one of the easiest ways that we think about applying a moment is that we have some force couple. So if I just, sort of, held onto your shoulders here and I wanted to rotate your body, I'd push, this axis, I'd push this shoulder, I'd pull that shoulder, and I'd rotate your body that way. So that is called a force couple because I can apply the same force on both sides, and that's just going to rotate you about your axes, right? So that's helpful for calculation. In that case, if you had a force couple in this way, you just say F times D. I have a cat here. Sorry, he wants to be in the video, I guess. So so now what we want another way of thinking about that is that I have some axis of rotation about the center of this body, and I have d over 2 times f. But I have two of those, so I have fd, right? So that's another way of thinking about it with the r cross f notation. When we want to turn an object, you can see this could be a valve of some machine, and so we apply a force, and so you can see we apply a force to rotate that object. So we have the 30 newtons applied in one hand, 30 newtons applied in the other hand, both perpendicular position vectors, right? So that you're applying the maximum efficiency there of turning, and that would give us 30 newtons times 0.4, and that would be our moment. Now we can apply the same moment in a different way by applying this a larger force at a smaller distance. Now that might not be the easiest thing to do, and it's much less efficient, but we could apply 40 newtons at 0.3 meters, and that would give us the same moment. So it would be much easier to come out to the outside or even larger distance and apply a smaller force to rotate that object. And that's a force couple. When we do the cross product, and this is just getting into the math if you don't remember from your physics, we have C is equal to A cross B. Now another way of doing that is that we have AB sine theta times some axis of rotation, or the U sub C, right? So that's the axis of rotation. Now, so this one, we put our thumb in the direction of the rotation, and we curl our fingers from A to B, and that angle theta is measured that way. So this is how we get that right-hand rule, the sense of rotation, plus the math behind that. Now, another way of calculating cross product is just setting up the determinant here. A cross B is equal to ijk in the upper row, a x a y a z in that second row, bx by is bz in the third row, and you can just calculate the cross product that way. Now, if you recall, though, there are some good sign rules that help you to keep up with, as you take the determinant, what are the signs as you go and you multiply out those terms. A cross B is equal to some I, J, and K components. So you can see on the left side here of the slide, we have for element I, for element J, for element K, we have the three components in the different areas. So when I multiply out, or when I try to solve for what is my I component, I start with I, and you can see I circle it there in the pink. And then I cross out the upper row and the first column, and then I make my first multiplication, AY times BZ, and then I have a minus AZ times BY. So that's how we solve for the I component. Now, the J is the same, except when I multiply by J, I have a negative out front. So I'm circling that J component there. So J, and then I'm going to cancel out that middle column where J is, and the first row again where J is, and then we're going to multiply out the rest of it. So AX times BZ, following the red arrows, minus AZ times BX, right? And you can see how the answer for that J term comes out. For the element K, we do the same thing. You see I circle K in red there. Now the first row and the last column are out from the equation, so I have the K term, then our K axis, then I have AX times BY minus AY times BX. So this is how we go through the multiplication of the terms to get the cross product. When we calculate the moment at a point, let's say O here, that's equal to R cross F, and then we set up the cross product in I, J, and K. Now F, the force F, can have many different directions, or different components. So the force F here has Fx, Fy, and Fz components, and then we have those will be put into this into the cross product, the R cross F. We also need to determine typically the position vector for R. If I wanted to represent many forces and or moments about a point, I can simply sum them up, right? And force F1, F2, and F3 applied at positions R1, R2, and R3. These will give you a moment resultant, and that's specified by the MRO here, the moment resultant about point O. To be able to get that, that's just the summation of R cross F. So that means I have to R1 cross F1 plus R2 cross F2 plus R3 cross F3. And that's equal to the moment resultant at O. Here we have a force that has components F1 and F2, and it has a resultant F, right? And the distance from point O to that force line of action is R. So how we do the cross product, you know some of the principles of this already, I'm sure. R cross F1 plus R cross F2 is equal to R cross F1 plus F2 is equal to R cross F, right? So whether I break a force into its components or not, it's still R cross F. So it's still going to give me the same moment. Here, if I wanted to take the moment about an axis, then let's call that axis UA. This in the unit vector direction UA. So I can put my thumb in that direction of UA, and then I have the force F applied at some position R, right? So you can see in this one, that's going to give me some moment resultant R cross F about the axis A. Now the way I can do that is the moment is equal to UA dot R cross F, right? So we have a bit more to work out here, but I can take the unit vector components, and I'm going to put those into the first row and determine the cross product, just as we did if we had I, J, and K. We're going to use this unit vector instead, and that will give us the moment about a specified axis. And that's really helpful for a lot of problems. So again, we can calculate the resultance of a force in a couple system through this method. So the force resultant is equal to the sum of the forces. The moment resultant is equal to the sum of the moments, right? And you can see here that we have the different ways of thinking about that. So one of them is that we can have a force at some position R, and second is that we can also have concentrated moments applied. So we can add R cross F, so forces applied at some position R, and we can also have concentrated moments applied, and we can add those components together, right? So when we are looking at the resultance of a force and a force couple system, so we can sum the forces in the X, sum the forces in the Y, and we can sum both R cross F plus some concentrated moments. So let's work out a few problems to get started here. And so these are example problems that it's great to interact on and then to practice what you've learned.
So now we want to practice calculating moments in 2D so that we can understand how the previous equations that we've explained, how they work. And so we'll start with a 2D problem, and you can look on the left side, where a 100 Newton load is applied to a cantilever beam, or a beam that has a fixed connection at O and is free at the tip of the cantilever beam. The 100 Newton load then, when it's applied, results in a moment at point O. And so we want to be able to calculate that moment. And so how can we start to begin doing this? Is we can come here and say, well, this is the moment is equal to R cross F. Well, that gives us the shortest distance, or perpendicular distance, to the force line of action of the 100 Newton load. So here's that force line of action of the 100 Newton load here, right? Here's point O, and so you can see here we are with this perpendicular distance here. So what is that distance? That's 2 meters. So we can say M is equal to 2 meters times 100 newtons. Now, it's helpful to know what directions these things are in, so that we know what we're talking about. So we usually would start with a coordinate system, and that's helpful for anybody who's looking at our work. So this is X and this is Y. So you have the 2 meters here, and that's the distance from point O to, let's call this point P, right? So we would have calculated that, and we would have found that position, or I should say distance vector, that distance vector would be pointing in the I direction. So we could have said here 2mi, right? And then we would say we have 100 newtons, and which direction is that pointing in? That's in the y direction, so that would be j, but it's in the negative j. So we have we would have j here, and then this would be negative 100 newtons. So then we want to calculate which direction is the moment is. So if we have ij, then you would have I cross j is equal to k, right? So that means this is an mz. So mz then is equal to negative 200 Newton meters in the k. So that means that you're, if you use the right-hand rule here and you curl, actually you can put your thumb out of plane here, you curl your fingers in the direction that the 100 Newton load would apply at point O to make that beam deflect downward like is shown here. So when you see that beam deflection downward, it's making it curl in that direction. So you can put your fingers in the x direction and then curl downwards in the negative y direction. Your thumb would then point into the board, and so, or into the screen, and that means that you have that negative moment in the k direction. So that's just a little bit more on what you're doing here. Let's look at the problem B. So now we want to know what is the moment that the 50 Newton load is applying at the point O. So we're going to do the same thing as we did before, where we have the moment is equal to R cross F, right? And so now the question is, what is the distance? What is that perpendicular distance to the force line of action? So you can see here the force is a 50 Newton force, and you see this dashed line here, that's the force line of action. So we want to calculate the distance from point O to the force line of action. Well, that's easily this distance here. Okay, so that's 0.75 meters as it says over here. So so this would help us to calculate what this moment is. Now it's helpful again to know which direction that the moment is in, so that you can calculate it just like we did over here in this problem. The moment here is equal to the 0.75 meters in the negative j direction, and then we have the 50 newtons that's in the negative I direction, right? So that would be applying a J cross I. So if you remember, I, J, K. So if you're going this way, you're going to have positives, and if you're going this way, you're going to have a negative. So the M then is equal to, you know it's going to be a K, so this is an MZ about point O. And this is going to be the 50 times 37.5 Newton meters in the K, in the K direction, right? And that's going to be negative also, because you're applying that moment. So J cross I is negative K. Now you could have easily calculated this in a slightly different way, and that would be that you did just very simply, you already know which direction that this beam is bending here, right? And so you see 50 times 0.75, so you know the the sense of the moment, you know which direction that it's in. But if you're going to calculate it through the numbers without guessing, which is usually easier, then you're going to calculate it this way. If you wanted to set it up in a matrix form, you just do something like this. M is equal to I, J, K. Then you set up R, and R would be the distance from the P to this O here for the moment I, J, K, and then we would have since we have the components of P minus the components of point O, and this is 0, 0, 0, so we just have the coordinates of P, which would be 2 meters minus 0.75 meters and 0. And then the next one you'd have the 50, but it's in the I direction and it's negative, so negative 50 newtons here, and you have 0, 0, 0. So as you take the cross product here, and you look at I, right, and you would cross out these two, and you say, well, this is 0 and that's 0, so there's no moment in the I direction. You take the J component, right, you cross out this one and this one, this would be 0, this cross then would be 0, there's no component in the J direction, and you have the Z, and then you have here's the K, cross out the first row, the last column, this is 0, and then you have negative, so Z about the O is equal to negative negative 0.75, and that's a Newton meter. Sorry, that's a meters times negative 50 newtons. So so you can see how this is going to come out exactly the same as we've calculated a second ago, and you can see how the negative, negative, negative becomes then finally the negative answer that we calculated just a second ago. So that's a few ways of working it out. It's easy enough in this problem, since you have nice perpendicular distances, just to say 50 newtons times 0.75, and we know we're in this orientation, so that's negative m. So you need to visualize it. You also need to be able to calculate it, and it's nice to be able to calculate it in a few different ways. Okay, let's do another few calculations here. So we can work on this problem C over here. I think it's easiest to do, since we've done it twice, it's nice to do this in a slightly different way. So let's just calculate the moment is equal to F D, and D has to be a perpendicular perpendicular direction in this case. So we already know the sense of the moment is this way, because it would tend to move the beam this way, and you can this way, so you can tend to see how that's going to rotate this member. Okay, so what we want to know is what is the perpendicular distance from point O to the force line of action. Well, that would be, if we drew a nice straight line this way, that would be this total distance to the force line of action here. All right. So how do we calculate that? So we know we have this distance is already given to us as 2 cosine 30 degrees for feet. All right. So this would be the moment is equal to 40 pounds times 4 feet plus 2 cosine 30 feet. All right, so there's force times a distance. Now it's still nice to give which direction that it's in, and you know that if you take that moment and you put your thumb into the screen and you curl your fingers in the direction of the force, this is you're going to see that your thumb, that this is the right orientation or the right sense of that moment of the 40-pound load about 0.0. So that's helpful, because then this becomes a negative, right? And then this is the k axis, and this is a mz, so that's a z about 0.0. And it's helpful to give these subscripts so people know what we're talking about. Again, it looks like that negative is missing now. So okay, so that's negative. What? Okay, so so you can go ahead and calculate that, but this is how it would be done. Okay, so this is the last one. So you have this member that's curved at the end with a 45-degree angle here, and you can see the 60-pound load is applied such that the member will deform into this direction. Now this, you can see, this is a positive moment, right? Now to know this one, we want to see what is the distance from point O to the force line of action. So here we have again the force line of action, 60-pound load, and we want to know this distance here from point O to the force line of action. So this is already given to us as 1 sine 45 degrees times feet, and that's how you begin to calculate the moment. So the moment, we'll do the FD this way, is equal to 60 pounds times 1 sine 45 degrees times feet. And you can go ahead and calculate that out, but this is how it's done. Is it in the positive or negative? You can see the sense is already correct for this one, so that means you're going to have to, using the right hand rule, your thumb would then be pointing out of plane. So this is how this moment would then be calculated, and I let you calculate that by yourself, but this is how it would be done. Now let's say that we want to calculate the moment that the tractor can apply to the tree about point O. So if we want to calculate that moment, we can begin by calculating R cross F. Now it's good to visualize what that means. So you can see this figure on the right here. You can see the tractor, you can see the tree. Now there's a distance from point O to the tractor, that's RB. Now calculating to the force line of action, there's 2 points that you know that are defined from point O to the force line of action. That would be RB or RA. So you can calculate both points are on that force line of action. So you can calculate RA cross F, or you can calculate RB cross F. So when we do that, we should be able to get the same moment MO, the moment about point O that the tractor is applying to the tree. So how about we go ahead and do that? And so what we're going to do first is I'll delete this right side so I have a little bit of space to write that you can see, and then we're going to calculate the moment using RA cross F. Now when we are solving this problem, we also we need to calculate the unit vector UAB such that we know the components of F, right? So we can we can first start with ROA or RA, and then we'll go to solve for F after that. So to calculate RA, we have the coordinates of A. So that's 0 meters minus 0 meters in the I. And we have 0 meters minus 0 meters in the J, sorry, let's see, in the J. And we have 12 meters minus 0 meters in the K. So this is the position vector. No wonder why it says RA instead of ROA, right, from O to A. So you can see this is 0, 0, and 12. Okay, so this is RA. Now, if we want to calculate F, we're going to have to take the components of B and subtract from the take from the coordinates of B and subtract from the coordinates of A. So let's do that. So that will be RAB. RAB is equal to B is, let's see, 4 meters in the X, and then we're going to subtract by 0 for the coordinates of A. So this is the I, and then we have let's see, the Y direction. So we have 12 meters, and then we have at point A, we're at 0, so this is the J, and then we have the K, so that's the tractor is on the ground at point B, so that's 0 meters in the Z direction for the tractor at point B, and then we have to subtract from the Z coordinates of A, so that's minus 12 here, meters in the K. So it's easy to see that this is just going to be the minus 12 here for the RAB. The next thing to do is we need that unit vector UAB. So that's equal to the RAB divided by the magnitude of RAB. So then we have to solve for the magnitude of RAB. So let's do that. So the RAB magnitude is equal to the square root of 4 meters squared plus 12 meters squared plus 12 meters squared. So this will equal 17.4. So magnitude RAB is equal to 17.4 meters. All right, so now you'll have the unit vector calculated that way, and we can then go ahead and multiply everything out. So this for the moment at O. So now we're going to calculate the moment. So the moment is equal to, okay, and just trying to make this a little bit large here to calculate the moment. So we can see we need to have RA are the components of RA. So that's 0, 0, and 12. And then we need the force vector after that. And again, so these are all moments. The force vector is going to be in kilonewtons. So we'll have in the I, we're going to have 2 kilonewtons divided by the 17.4, which is the magnitude of RAB, and then we have to have the components of RAB, so 4 meters. Okay, again, we're going to repeat that. 2 kilonewtons here divided by 17.4 meters, and then the components of RAB, so that's 12 meters in the J. And for the K, 2 kilonewtons divided by 17.4, and then the components of RAB in the K direction, so that's minus 12 meters. Okay, and so this is how you can go about calculating these parts. So MO, we would start with the I component. So we would cross out these two parts. We have 0 here, and then we have the MO is equal to, cross out these two parts. We know we're in the I axis. This is 0, and then we have minus 12 meters minus 12 meters times 2 kilonewtons times 12 meters divided by 17.4 meters in the I direction. And we have to calculate the next one for the J. So we have the J component, and we have 0 here, and then we have minus 12 meters times 2 kilonewtons. 2 kilonewtons times 4 meters divided by 17.4 meters plus the K. And so this would be 0 and 0. So then you can start to calculate that part. Now we're missing just one part here, which is when we're calculating the J component, we have the IJK. So if we're going this way, it's positive. If we come back, it's negative, and so I to K negative J, right? So we have to then multiply this part by a negative. So I'll let you calculate this out, and this will be the MO term for this way of solving the problem. So let's then we can calculate the last part of the problem, which is if we wanted to calculate it from the RB term. So what would that look like? So we would have to calculate MO is equal to IJK, and we still have F being the same, but we have a different vector for the direction vector because we have RB. So to calculate RB, and to say that if we have RA cross F or RB cross F, that would give us the same MO, or the same calculation for the resultant moment. You have to calculate it out to make sure that that's the same. So the components of RB are the coordinates of point B. So we have in the X direction we have 4 meters. In the Y direction we have 12 meters, and in the Z direction we have 0 meters. For the force, we have the exact same thing that we have here. So 2 kilonewtons times 4 meters divided by 17.4 meters. 2 kilonewtons times 12 meters divided by 17.4 meters. And the last one, 2 kilonewtons times minus 12 meters. Make sure everybody sees that's a negative. Divided by 17.4 meters. And we would calculate the cross product from this one. So this one we would calculate, and you can see that we should get the exact same answer, but let's go ahead and calculate. So in calculating this last part, we would have just let's go through this one. So we're going to have 12 meters times 2 kilonewton times negative 12 meters divided by 17.4 meters. This is for the I direction. Then we'll have a negative for the J, and that's 4 meters times 2 kilonewtons times negative 12 meters divided by 17.4 meters in the J. And then for the K, we're going to have two terms. So 4 meters times 2 kilonewtons times 12 meters divided by 17.4 meters. And then we're going to subtract out 12 meters times 2 kilonewtons times 4 meters divided by 17.4 meters in the K. Now the interesting part about this is that these two parts are going to cancel out to 0. So we would get the same answer that we had over here for just I and J components for the moment. So no matter which way you calculate it, any point to the force line of action, you'd have the same answer. So if you calculated it with RA cross F or RB cross F, it would be the same answer, since both RA and RB give you the distance to the force line of action from point O. All right, so that's just proving that point through a real problem. So we would like to calculate in problems that have multiple forces the moments about a point. In this problem, we have two forces about two different points, and we'd like to calculate the moment about point O. So how do you do that best? And so the moment m about O is equal to the summation of R cross F. Well, that's a nice form here, but we need to translate what it means in this problem. So let's say, well, that's equal to, in this problem, RA, so the distance from O to A, we'll call RA, cross the F1, so that's this force here. So this is the force line of action here for the force F1 given by the force vector here in pounds. Plus, now we have here B, and so we should have try that again. RB and the RA. So so that would be RB cross, and then the force here, so for the force line of action here, is the F2. So F2, so RB cross F2. So this is how we would calculate the moment in this case. The only issue is that we don't know yet what RA is, and we don't know what RB is. And then we'd have to calculate the cross product twice, and then add those components together. So this is how we would go about doing that. So let's first we calculate RA. And this is just going to be right from the coordinates of A. So the coordinates of A then are, say, 0I plus 5 feet in the J plus 0 in the K. All right. And now we can already go ahead and calculate this RA cross F1 by this IJK 0, 5, 0, where this part is all in feet, and then we have the F1 term, so that's negative 60, 40, and 20, and these parts are all in pounds. Okay, now to calculate this one, we would then have for the I term, so we'd cross out these particular parts, and we'd have 5 times 20 minus 0 times, well, 40. So we have 5 times 20, well, 5 times 20, and this is foot pounds in the I, plus, and then for the J here, we cross out this column and this row. We have a 0 times a 0 on the other side, so plus 0J. And then for the K term, we have, so K term here, we have a 0 and then minus 5 times minus 60. So minus 5 times minus 60 in the K direction. Okay. So so this is, we'll call this term an M01 for the moment due to the force F1. All right. And so that's this moment. M01 is equal to all of this. So now next we'll calculate RB, and this is equal to, let's see, the coordinates of B. So we have 4 feet in the I direction for X, right? And then we have plus 5 feet in the J direction. And then we have minus 2, because we're in that Z-axis, minus 2 feet in the K direction. So this is RB. Now we're going to do the same thing, and this will be MO2 for the moment due to the force 2, is equal to, and we're doing the same thing here, IJK, the RB for feet, 5 feet, minus 2 feet, and then 80 pounds, 40 pounds, and negative 30. All right, so this is how to set up setting up the cross product for this one. And now calculating here, MO2 is then equal to 5 times, so for I, 5 times negative 30, 5 times negative 30, and then minus, coming the other way, negative 2, 40. Okay, and this is for the I direction. Then we have negative, and we're going to have the J direction next. So that's going to be J 4 times negative 30 minus negative 2 times 80 for the J. And then for the K, we have 4 times 40 minus 5 times 80 in the K. All right, so now all we're going to need to do is add up these I, J, and K components for MO1 plus MO2. So in the end, this one is just MO1 plus MO2 on a component by component basis. So let's do that next. So then MO is then 5 times 20 plus 5 times minus 30 plus 80. And we need to make sure we keep up with everything, but this is all in foot pounds. And this is an easy way. Just put everything in brackets, put your units at the end, and then this is in the I axis. And then plus 4 times 30 minus 160. Foot-pounds in the J. And then finally we have the K-axis. 5 times 60 plus 4 times 40 plus 5, minus 5 times 80 in the K-axis. So finally, MO is equal to 30 foot-pounds in the I, minus 40 foot-pounds in the J, plus 60 foot-pounds in the K. So you can see how we calculate everything from the summation of R cross F. That's how you're going to use that. And we translate that to each component, right? And then we can nicely label each part of those, MO1, MO2, and then we're adding that up. So after we've conducted the cross product for each of those forces, we can calculate the moment due to F1 and F2 about 0.0, and that's very helpful for a lot of problems. So so try to practice this one a few times. Usually this is a problem like this will be on my first exam. I really love this problem because it's so instructive for teaching on how to solve for moments and problems, how to calculate the externally applied forces to the moments at another point. And so this is you have a force here. So we have the force F here. Now this force F is acting on this point, and we want to know what is the moment due to this force about point O and its orientation. So a lot of times when I give the problems like this and I say, okay, what is the moment due to the force F at point O, the first things I would ask is, what is its orientation? So to find out that, we have to really think about the problem. So the first thing we might do is what a lot of people think is we want to calculate from the point that we want to know that moment at to this a point where the force is applied. Let's call this point A. So a lot of people will start to work on a problem like this, and they want to calculate this distance, for example, RA. So to calculate RA is a little bit tricky because we have to start dividing the circle into parts and finding the x and y components, etc., etc. It takes some time. And you don't have the time many times on an exam to start calculating all these things and finish a long exam. So there's you have to be a little bit smarter than that when you're going to solve some problems. So the first thing that you learn when you do these problems is that you have to take the force line of action down here, right? And you need to calculate the perpendicular, or I should say the shortest distance, perpendicular distance, from the force line, from the point O to the force line of action here. So the distance that we're actually looking for is this distance. So it is this distance. And so what is this distance? That's just the radius. That's just 3 meters. So I don't actually need to calculate if I'm trying to calculate the moment due to this about point A. I can just calculate it about this point. Let's call it, I don't know, well, I guess we can call it B, right? We need to calculate it about point B. And that's much easier to do, so we can calculate it that way. Now I can translate this force to this point and say, well, it has 2 components. So here's the force. It has 2 components for the x and the y. So let me just kind of translate it here for a second, just kind of to visualize things. So we have the force in the x direction, and we have the force in the y direction. Now, which of these is going to cause a moment about point O? And obviously, you can say, well, it's not the x, not that component in the x direction, because it goes right through point O. So there can be no moment due to fx. So we only want that y component. So to get that y component, we want this, this side. So this is this distance would be fy is equal to f sine of 45 degrees. All right. So now I believe we have there was a force given here of 500 newtons. So so you can multiply it out here, but the easiest way to calculate the moment then is just the moment about O in the z-axis, and this is going to give you a positive moment, but you can go ahead and calculate it, is r cross f. So this one we can do rb, where this would be rb cross f. So it's easy enough to do that way, but this is 3 meters in the I direction, and then we're going to have just the y component, or we could say j component of the force F. So that's 500 newtons sine 45 in the j direction for this one. So I times j is a positive k. So this MOZ is equal to this is equal to 1500 times sine 45 degrees Newton meters So this is how you can go about solving a problem like this. I love this problem again because I see a lot of times students are they start to jump in and they start calculating RA, right? This kind of difficult, more difficult geometry to find instead of just saying, hey, 3 meters, RB, right? So remember, you have that you're calculating the distance to the force line of action and not just to the point application of the force. All right. So let's say we wanted to calculate the moment about an axis. Well, some of the previous problems they don't have that, but it may be that you have like this problem, a hinges along some axis, like a door, or like some cantilever beam, maybe a retractable one that's outside of a restaurant or a home, or something to protect from the rain if it's raining, something that you could lift up or put back down. So you might want to calculate the moment about an axis instead of a point like we've been previously doing. So the way of doing that would be that we have a different way of doing the moment calculation. So the moment about some axis is equal to the unit vector about that axis, the dot product with R cross F. So this is a convenient form for this particular problem here, but we need to translate this to this particular problem further. So for example, the moment about the CD axis here, right? So the CD axis is equal to the unit vector along the CD axis dot the R cross F. So this is any vector from the axis to the force line of action. So we have a few vectors that we could choose from, a few distance vectors that we could choose from for doing that. So we could choose from C to A, we could choose from C to B, we could choose from D to B, or D to A. I think the easiest is from C to A. So what we're going to do is we're going to do that one. So we're going to do R, C, A. So from C to A. And then we're going to cross product. We're going to have the cross product with F. Now, right now we don't know the magnitude of F, so this is just going to be we're going to have to calculate both. Well, we don't have the magnitude, but we'll calculate the unit vector of this F. So this F we can give a subscript as well. This one goes FA to B. So we're going to have to calculate the unit vector from A to B and then multiply by F to get both magnitude and direction. So let's try to get started to calculate how to calculate the moment about axis CD. So let's first calculate the unit vector along the CD. So this is UCD is equal to RCD divided by the magnitude of RCD. So let's calculate RCD first then. So now C has the units, C has the coordinates of the origin. So the only thing that we have here are the coordinates of D to show and to take a look at. So RCD as then equal to 0 I plus 8 feet in the J because you can see here's the j-axis and here's 4 feet and 4 feet. So here's 8 feet in the j. And then for the k direction, we have plus 6 feet in the k. All right. So this is RCD. So calculating the magnitude of RCD is equal to the square root of, here we go, 8 squared, 64 feet squared, plus 36, you see, 6 squared, 36 feet squared. So this is 100, so then this must be equal to 10 feet. So then UCD is equal to this divided by 10, right? So that's 0I plus 0.8 J plus 0.6 K. So that's UCD. So now that we have UCD, let's calculate RCA. RCA. C to A here. So we need this RCA. So along here. All right. So because the components of C again are 0, so all we really need is the components of A to calculate RCA. So that's going to be 6 feet in the I plus 0J plus 0K. Now that was relatively easy. And now we want to calculate the unit vector for the AB so that we can then multiply by F, and we have all of the components of F to complete the equation. So let's look at the point B. Point B is at 0 in the x direction here, so because it's on this wall here, so 0 in the x direction, 0, and 4 feet in the y direction, and then we have 12 feet, so the 6 plus 6 in the z direction. And again, the coordinates of A here, right? We don't have anything in the y and z direction, so we just have 6 feet in the x direction, and then 0 and 0. All right. So then RAB, or I should say RAB is then equal to minus 6 feet in the I, so 0 minus 6, right? 4 minus 0, 12 minus 0. So this is 6 feet in the I plus 4 feet in the J plus 12 feet in the K direction. So that's RAB. Now we need to find the unit vector, so we're going to have to take the magnitude of RAB. So this is equal to the square root of 6 squared, 36 feet squared, plus 16 feet squared, because 4 squared, and then plus 12 squared, 144 feet squared, is equal to 144. Sorry. Is equal to is equal to 14 feet. So now for calculating the MCD, setting it up is one of the most instructive things that that we would do this whole problem for. So let's come back here and we say MCD is equal to and then here on the top line for the determinant and calculating the cross product, we're going to put the components of UCD. So that's 0, 0.8, and 0.6. Now the next line we have the direction vector RCA. So that's here 6, 0, 0, 6, 0, 0, and yes, this is feet because it's a direction vector. The last thing that we're going to have is the unit vector of for the force from A to B times the force. So we can do, you can see this is the force here, or sorry, the components of the force would be minus 6 divided by 14. So minus 6 divided by 14. Again, because your unit vector AB is equal to RAB divided by the magnitude of RAB. And we're going to have to multiply this by the force magnitude, but we don't know what that is, so we'll just leave it as F here. And then again, we'll have in this next one 4 divided by 14. So 4 divided by 14, again, times F. The last one is 12 divided by 14, so 12 divided by 14 times F. And in calculating this, the MCD would then equal 0I, and then because this is 0, so everything you multiply is going to be 0. And then we're going to have minus for the J term. So the 0.8 times 6 times 12 over 14, and then you have 0. So 6 times 12 over 14 F, and this is the J. And then we have to calculate the K, so this is 0.6 times 6 times, so 6 times 4 over 14, and then minus 0 times minus 6 over 14, so that's just 0. And then we don't forget you have to multiply by the force magnitude, and you have K here. So this is how, and you can calculate the rest of this one, but this is the moment about the CD axis. So this type of problem is very nice for calculating the moment about an axis. But yes, a lot is required to try to calculate that. We have to calculate unit vectors for the CD, unit vectors from A to B, and the distance from C to A, just to be able to go through and calculate this problem. And then, of course, knowing how to set that up by setting up the cross product, the dot product and cross product here is one of the key components of getting the answer here. So try this out on some other problems and homework problems, and expect a question like this on your first exam. So if there are several forces acting on a body, like in this case, we have some type of a bracket, and we have several tension members coming out of that bracket. So the force 3 kilonewtons applied at some 30 degrees, 5 kilonewtons applied at some angle, and then we have 4 kilonewtons applied vertically downward.
Now, when we apply these forces, if we wanted to calculate the moment at that's at O, where we're attached to the wall, now one of the reasons we might want to do that is to see if the bracket could be fractured or broken from the wall, which you'd learn about a bit later on in the semester. But we would want to know what is that force on the wall, applied at the wall from all of these tension members. So the way of doing that would be the summation of R cross F. The easiest way to calculate that, though, would be to break each force into its components in X and Y, so that we could calculate the distances with rectangular components, right? So, like for example, the 3 kilonewtons there, we can say 3 kilonewtons sine 30 degrees, that would be the vertical component, and we have 3 kilonewtons times cosine 30 degrees, that's the horizontal component, and so on for the rest of the systems here. Each one, it's relatively easy to calculate its distance, and then we can calculate in rectangular coordinates each of the components of the moment and add them up component by component, the I, J, and or K components if it was 2D or 3D problem. So you can see here, it's relatively easy to calculate those distance in rectangular components, but we'd have to still break those forces down to their components to be able to solve that problem quickly and easily. So that, if you go through that summation, you'd end up with a moment applied, and then you could take that force and then show that all of the forces transmitted at point O, and that would be the force resultants. That's the total force. Summation of all X, summation of all Y components, and shown in their components here. And then you can calculate the angle by using a tangent, and you can see which angle is this force resultant from the horizontal or vertical. And then you can also do R cross F to calculate the moment resultants. Some of these problems are really similar, and so whether I did it with a bracket or some type of a piping or other system, then how I would go through calculating the moment applied at the fixed end O would be the same, right? But I could also simplify certain problems. For example, do you see the force couple on the end of this member? So the 200 newtons times 1 meter, right? So that would be 200 Newton meters, and I can replace that system with a concentrated moment at the end of the member. And since it's not going to add anything to the total force resultants, because I have plus and minus 200, then I can directly place that moment on O, 200 Newton meters, right? The rest of the moments are exactly the same as you would do R cross F, but it's good to see how you might be able to simplify a problem. And you can see that, see the result of that here. And so you can place that, all the sum of the forces in the X, force resultant in the X direction, the sum of the forces in the Y, the force resultant in the Y direction. You can solve for theta by taking the tangent inverse of the Y and X components respectively. I hope that you got a good chance to learn force and moment resultants in this lecture, and that you can go back and practice problems. If you have questions, we will have an interactive session in the first few days of the class to go over this content. So thank you very much.